Bună ziua. Hello everybody. So today we're going to discuss about bag of words and the bag of visual words. Sorry for the delay. It was a bit caused by the previous lecture. So we have a lot of slides today and a lot of things to present. So today we're going to discuss about these models that, at least in the case of the bag of visual words, we use the k-means algorithm. So part of this lecture will be about k-means, but only briefly. We're going to discuss more about k-means and unsupervised algorithms starting from next week. So yeah, until I start, just let me know if you can hear me well and see my screen sharing, so that I can start the lecture. Okay, perfect, thank you. So the agenda will be to discuss about object class recognition and give you the bigger picture, and we discuss what is an object class, and then we build our way towards the bag of visual words model, which is actually borrowed from natural language processing, where we use the bag of words. So we first introduce the bag of words, and then we go back to image processing and discuss about histograms for feature representation, and then the better approach, which is to use a bag of visual words. So I'm doing this presentation to let you have an alternative for your project. So you can either use neural networks that are based on end-to-end training, and you can also try this approach that is based on let's say handcrafted features. So I'm actually going to this summarizes the most common handcrafted approaches that are used in image and natural language processing. So first we discuss about object classification and related tasks. So in an image, the object classification task is about what you see in this image, and you can think of all the objects you can identify, and yeah, there is clearly not a clear boundary where you can stop at about naming object classes. So you can name the most obvious things like the man, the bear, the bunny, let's say the trees, but then you can also think about the grass on the ground, the leaves, the camera that the person is using. We can also think about, I don't know, the socks, the shoes, the t-shirt, and the pants, and so on. So yeah, naming the object classes is related to object classification, and also this is related to detection. So for to properly recognize the objects, we also have to tell the location of objects in images. And we can distinguish the objects based on various features. So for example, all the objects can be, I don't know, represented in this space where we have features. Let's say correspond to questions such as, is it dangerous, is it alive, has tail, and so on. And based on this question, we can obtain these questions. We can obtain a vectorial representation from all the answers. And we can use this representation to, yeah, this is conceptually what we want to do, and then we use this representation to solve tasks such as object class recognition. So this refers to can be posed in various ways. So as a verification problem, so we can ask, is there a light pole in this image? And we can have a binary answer, yes or no. So we see here two light poles. So in this case, the answer could be yes. Then we also have the object detection task. So where is the pole? And we have to um, yeah, provide the locations for this object. So this is called localization. We also have identification. So this is the task of naming the specific instance of an object class. So which palace is this? It is the Potala Palace on Tibet. Then we have region classification. So for various regions, semantic regions that appear in the image, we have to name the classes. So here we have trees, a banner, building, mountain, castle, people, shops, shoppers, and so on. Then we also have a different task, which is called scene classification. So this can be an outdoor scene or an indoor scene, or it can be an urban scene or a wild scene, and so on. Okay, so we're not interested in doing instance level object recognition. So for example, in this image, we're not interested that this is the car of a specific person, but we're interested in generic object recognition, so to recognize all instances of cars. So this is the more difficult task in vision. So if we want to recognize a very specific object, we can identify some particularities to identify it. Perhaps the license plate number could be most indicative for cars. But yeah, we're interested in recognizing instances of objects that can have various shapes and colors, so there is a high variability in appearance. So yeah, to formulate the task, so given a small number of images with an object class, we need to recognize the instances of the object class by assigning the correct object class to each instance. And about the level, so we call it generic recognition, as we refer actually to this hierarchy of classes. So the classes of objects, they have a hierarchy. And if we think about instance level recognition, about recognizing specific instances, for example, a dog named Max, that is a Labrador, is a specific instance of an object class, of a larger object class that is known as dog. So typically the task refers to the level where we can mentally assign an image to the specific object class. So if we look at this specific to generic hierarchy of classes, if we're thinking about, I don't know, life beings, there isn't a specific image because this is too generic concept. And for animals, there isn't a single instance that can represent this class. But for dog, I think we can already build a mental image of a dog. So the highest level for which we can identify, mentally think of an image is called generic object class recognition. And we also have a more fine-grained level where we, for example, we want to identify races of dogs, so we go typically lower in this direction. So the interesting tasks are usually in this range of levels, base level or inferior levels that are related to fine-grained object recognition. So yeah, in the hierarchy of organization of object classes, we have these superior levels, the inferior level, and this base level. So this is the once again, this is the highest level for which we can assign a mental image. And this was proposed, this organization was proposed by Roche in 1976. Okay, so for this base level, there is a significant number of common attributes between member pairs, which can make us think of this mental picture. So having this enough attributes to build a mental picture is the base level of object classes. Okay, so this is usually the first level, also understood by children, and of course the similarity between inferior classes is larger, but the the it is not increasing with the same as from superior classes. So yeah, if you want to distinguish between different races of dogs, then there are very particular things that you can think of, like I don't know, um, skin color and I don't know, perhaps size of the body and so on. Yeah, so there are many examples of object classes, and the number of object classes is usually was studied in the literature, and Biederman proposed that the number of object classes is around 10,000 to 30,000. So this was done actually by consulting a dictionary and seeing how many of the things listed in the dictionary can be are objects. Okay, so this task works well for specific applications, at least with basic approaches that we're going to present today. So notable applications are in optical character recognition, like license plate recognition and postal code recognition, fingerprint recognition, face detection. So there are many devices that can now, camera devices that can now detect the face very quickly. What also works well is the recognition of textured objects and recognizing specific instances of these objects that have very similar features. Then we can also we also see applications in finding visually similar objects, so recommending objects that are similar. This can be used in product recommendation for online selling websites and so on. And yeah, in computer vision, the problems with object recognition are typically with respect to the intra-class variability. So inside a class, we can have large variability, and also interclass similarity between object classes. So these are typical problems, and because of these problems, we cannot apply a simple linear model to solve the task. So directly on input images, we need to extract some features that can generalize better to our object classes. Okay, so in perhaps one of the most basic tasks for image classification is to classify images into indoor or outdoor scenes. And this is not so easy because you can have outdoor scenes with buildings. So you may think first that maybe indoor scenes contain a square, a lot of objects that have rectangular shapes, but even in outdoor scenes you can find these. So you still need high level representations to obtain a good result. So usually the approach is to model object class recognition as a classification problem. So you're given samples with the two object classes, and then you obtain test images, and you need to assign labels to these images. So typically we use supervised learning for this task. So in the typical framework, we have images with different object classes. We extract some features, for example, color histograms, text tones, and so on. So today we're going to discuss about more of these feature representations that give us a robust visual feature representations, and then we apply a classifier on top of these features and obtain the final class labels. So far we presented several classification methods, so the purpose is not to present another classifier today. We assume that we already know this part, and we're going to focus on the feature representation. So we're going to discuss about feature representation for images and about feature representations for documents. Okay, so in the training stage, we have the training samples, we have the labels for the training samples, we extract some image features. The learning part involves learning a classifier on top of these image features, and then we use the train classifier to discriminate test time between new data samples. Yeah, so at the inference stage, we extract the same image features as the training time. So this process, this algorithm that is involved in extracting features is identical at test time. So once we extract the features, we obtain a vector that represents the test image. We apply the training classifier and we obtain the prediction for the test image. So this is how it works, and as I said before, we focus on the feature extraction part. So perhaps the first idea could be to use histograms with intensity of the pixels. So we have, let's say, grayscale images, and each pixel has an intensity between 0 and 255. So we can, from this image, we can build a histogram with, I don't know, by counting all the pixels that have a certain intensity level. So we obtain a histogram that looks something like this. So we have a vector with 255 components that can be used to represent an image. Yeah, so we can use different approaches to build histograms and to think of different features. So if we want to obtain better results, we can use either a joint histogram of these two features. So we count how many instances fall in each bin, or in this case we have independent histograms. So we have the histograms for feature 1 and the histograms for feature 2, and we have independent histograms that can be concatenated together. So this approach is better if we have a more dense representation. So if we have less data points, then independent histograms are probably more appropriate. And on these histograms, we can also apply clustering to obtain a representation. So we can consider the number of points falling in each cluster as a sort of histogram that is adapted to the two-dimensional feature space. And the histograms can be normalized to obtain normalized feature vectors for the classification part. The important thing is that we use the same cluster centroids in all images. And then after we obtain histograms, we can apply, for example, nearest neighbor models, or we can use distances between histograms that can be transformed into kernel matrices, and then we can apply kernel classifiers on top of them. So we have the, for example, what we can use here is the Euclidean distance, the chi-square distance, which is specifically designed for histograms. We also have the histogram intersection distance, similar to the histogram intersection kernel, and so on. So if we use histograms, for example, if we look at the image retrieval result for this image, we typically obtain images of cars that are visually similar to this object. So here we see red cars that are seen from the side and have a green background with some, perhaps some road under. So yeah, these are the most similar images in terms of color histograms. But if we want to do object class recognition, this is perhaps not the best approach, because if we want to have a recognizer for cars, then this will return inconsistent results for cars that are have other colors, or if they are photographed from a different angle, like frontal or back facing cars, and so on. Okay, so a few details about implementation. So there are a few parameters when we use color histograms. First, we can choose intervals. So in the first example, I showed you that you can build histograms from all the intensity levels from 0 to 255, but actually you can choose different size for the beans, as in these. So yeah, this is an example with clustering. In this case, you have beans that can be larger than that. So if you want to use intervals, it is faster, and it is applicable for smaller images. And if you want to use clustering, this is slower but applicable for larger images. And regarding the number of intervals, if you want to have a coarse representation, you can use fewer intervals. And if you want to have finer representation, so if you have many object classes and a higher variation of object classes, you can use more intervals. And regarding the distance metrics, the Euclidean distance and the intersection histogram intersection distance are faster to compute, while chi-square obtains better accuracy, and these are the most popular ones used in literature. You can also, of course, try out other distance metrics. Okay, so now the usage of histograms can obtain some better results than using the raw pixels, of course. But it still doesn't generalize so well to as I said, interclass variability. So for classes where we have objects of different colors, like dogs, cats, cars, and so on, you have high variability, intra-class variability, and your model will not, your histogram-based model perhaps will not work so well, unless your dataset is very large and contains all possible colors of cars, which is perhaps not possible. So a better approach would be to use a bag of visual words representation. But before discussing the bag of visual words representation, we present the bag of words representation for text. So here we try first to understand the basic concepts and how we use the bag of words in text classification. And then we discuss about the bag of visual words by starting from the basic model from NLP. So yeah, in NLP, the bag of visual words, the bag of words model, we have a set of documents, and all the words from the set are added into a vocabulary. So the vocabulary is a list with all the words in the document, and we assume that the list is ordered in some way. Let's say we use the alphabetical order. So after we build this vocabulary, we can obtain a bag of words representation for each document. So this is a histogram actually that counts how many occurrences of each word in the vocabulary are found in our document. Yeah, so if we look at this text representation, then we have we can build this bag of words. So the name of the representation comes from the fact that this histogram of words loses the order of words in the text. So once you build the text, the bag of words representation, you can no longer recover the original text. And other typical transformations that are made is to eliminate stop words, which are very common and can be not representative for I don't know, classifying documents or by topic or by sentiment and so on. So yeah, in this case, for example, if we want to do document retrieval, so I think perhaps the most popular application of the bag of words is in document retrieval. So we want, I don't know, for example, to use it in Google search. So we take the documents, all the documents from the web, we build a bag of words representations for them, and then when we search for some phrase, we build a bag of words for the phrase, and then we can easily retrieve documents by computing similarities between the bag of words of the query with the bag of words of the documents from our database. Okay, so in this example, we have this text from by Alan Turing, and we have the bag of words representation. So we eliminating the stop words, we keep words such as believe, and use, century, and so on. And once we have this representation that eliminates the stop words, if we search for some keywords in order to get this quote from Alan Turing, So let's say we don't remember the exact quote and we want to search for it on Google, and we remember some of the words. Then when we match the query with the document, we will find that I don't know, a web document that contains this quote is very representative because it contains all these three words. So it will return relevant documents. Okay, so yeah, this is an example from plays by Shakespeare, with different plays and the characters that appear in this plays, and also different words. And so for this play is represented by occurrence counts of how many times, or one way is to use one approach is to use the occurrence counts, the histogram, and another approach is to use a binary vector, so just see if this word appears in the document or not. So using binary vectors gives us the opportunity to find the results for retrieval more efficiently. So it's an alternative representation to computing the occurrence counts. Anyway, so this is the binary term document incidence matrix, and here we have the word Anthony that appears in display, and not these three, and so on. Then for the count matrices, we have the term document count matrices, and here we have the counts, how many times a word appears in each document. And yeah, each document is a count vector. So this count vector is also known as the bag of words. So essentially in this representation, we know all the words that appear in the document, but we cannot put back the document together because we do not know the order in which these words appear. So the problem with the bag of words is that we cannot recover the order of words. So the sentence "John is quicker than Mary" will have the same bag of words representation as "Mary is quicker than John," but these two have opposite meanings. So although they have the same vectors, conceptually they mean opposite things. So what we can do about this, so people have already done it in literature. We can recover the locations of words by using word n-grams. So instead of building a bag of words, we build bag of word n-grams. So if we use p-grams, we will have so each concept in the vocabulary will be formed of words like John is quicker than, and then Mary. And if in this case, in this example, if we use word bigrams, we can already have a different representation, because here we have the words John is, and here we have the word Mary is. So this pair of words are distinct. And another approach would be to use spatial pyramids. So this was studied and was proposed in our book published at Springer, and this idea was actually borrowed from images, where people used the bag of visual words, and in order to recover the locations of visual words and images, they proposed spatial pyramids. And instead of word n-grams, the main benefit with spatial pyramids is that they give you the rough location of words in the document, not so they recover maybe the global location, not the local location, but in terms of space, they have a more compact representation than using word n-grams. Okay, so we can build a representation for the documents using the vector space model. So this is based on assuming t distinct terms that remain in the vocabulary after indexing, so after removing stop words. And these are called index terms. And we think of these terms as orthogonal. So each term in a document or a query J is given by a real value weight W of I and J. So both documents and query are expressed as t-dimensional vectors. So the vectors have these are composed of these weights. So a query J or a document J here is denoted by D of J is equal to the components W1, J, W2, J until WT and J. So yeah, these are t-dimensional vectors and each component is a weight. So here we have a graphical representation. So document 1 is represented as 2 times T1, 3 times T2, and 5 times T3. And these are terms. So these are terms. Another document is represented like this. So we have another set of weights assigned to these terms. And then the query is represented like this. So in the graphical representation, the terms are actually different dimensions, and each document is a vector in this space. So this is why this is called the vector space model. So essentially this is equivalent to a bag of words representation so yeah, this is the graphical interpretation of the bag of words. So these are the vectors, and now we can think of computing these similarities between documents and queries. So is document 1 more similar to the query or document 2? How do we measure the degree of similarity? Do we use distance, angle, projection, and so on? So actually I think the most common way to do it is to use the cosine similarity or the scalar products. Okay, so first, how do we build these weights? So having a collection of n documents, we can represent documents in the vector space model by computing a term document matrix. So this is going into what we tried to explain intuitively before with the bag of words. So then an entry in this matrix corresponds to the weight of a term in the document. So here we, instead of using the actual occurrences, we will try to find a different component, a different way to represent the weight of a term for the document. So instead of just using occurrences, we're trying to use perhaps something else. and we will explain what we use and why in the next few slides. Okay, so we can also have some weights that are equal to 0, so it means that the term has no significance in the document. So this is the case when a term does not appear in a document, its weight will be 0. So all the weights that are higher than 0, it means that the term has some significance for the respective document. And by the way, I didn't mention before, but here if we use this vector space model, it is no longer necessary or mandatory to remove the stop words, because we will see that we can assign weights that can actually demote the weights of the stop words. So the first thing that we take into account is the term frequency. So the occurrence counts of terms in a document. So yeah, the term frequency is defined as the frequency, so it's the value f of I and j, that the term is the frequency of term I in document j. So we want to normalize the weight or the term frequency by dividing by the frequency of the most common term in the document. So this is to make sure that the frequency of the words do not are scaled with respect to the size of the document. So if we have larger documents, we will have larger frequencies. So in order to normalize the frequency, we divide it by the maximum frequency in the document. So this is known as the term frequency of a term in a document. So it's a value between 0 and 1. So for the word with a maximum frequency, or if there are several words that have the same frequency and that is equal to the maximum, these will have frequency 1, and all other words will have a frequency between 0 and 1. So first we take into account the frequency of term. Then what we want to do is to use these term frequencies perhaps for computing query document match scores. The problem is that we do not want the raw term frequency because, for example, a document with 10 occurrences of a term is more relevant than a document with one occurrence of a term. So the difference is not 10 times as more relevant. So this is not actually directly proportional to the number of occurrences. So we can also try to think of the document frequency. Actually, for example, rare terms should be more informative than frequent terms. So this is how, for example, stop words are modeled. So if we just think of the term frequency, the words that are more frequent are stop words such as the, and, of, in, and so on. So if you consider a term in the query that is very rare, for example, let's say the word brewery, a document containing this term is very likely to be irrelevant to the query. but still we do not expect this word to be very frequent, very often repeated in the document. But still, we want this word, this rare term, to be very relevant for the document. So, what we can do is we can use the inverse document frequency to normalize the term frequencies. So, basically, the terms that appear in many different documents uh, should be less indicative of the overall topic. So, for example, words, stop words that appear in all documents, say, let's say the word the or of, should be less indicative. So these should not have a big weight to represent a certain document. So we can think of using the document frequency. So this is computed as the number of documents containing a term I. So then we can normalize the term frequency by multiplying it with the inverse document frequency. So the inverse document frequency is uh, scaled with the logarithm. So it is equal to the number of documents divided by the number of documents containing the term I. So this is the document frequency. So we compute, this is the inverse document frequency, is the logarithm of the number of documents divided by the document frequency. Okay, so if we then we can combine these two measures, the term frequency and the inverse document frequency, into a combined metric, which gives us the final weights for how representative the term I is with respect to document J. So in the term document model, these instead of using the actual occurrence counts, we use these weights instead. So the main concept is that if we have a term that occurs frequently in the document, but rarely in the collection, it should have a very high weight to represent the documents. Okay, so this is perhaps the most common approach in literature. There are also others, but this term frequency inverse document frequency, or shortly known as TF-IDF, is one that works very well in practice. So um, this has also been used in the bag of visual words, and it seems to bring performance improvements. So instead of using the actual occurrence counts, we can use this approach. Okay, so now we know how the weights are actually computed with TF-IDF, and then we have this vectorial representation. So here, actually, instead of occurrence counts, we can think of these as these TF-IDF scores. So we represent the documents and the queries like that, and then we just compute the similarity, the cosine similarity between the query and each document to obtain a similarity vector and return the documents in order of relevance. Yeah, so this is kind of behind the scenes to what happens in a document retrieval system such as the one used by Google. And now we go on and move our discussion back to object class recognition, where we can think about applying the bag of visual words for this task and try to figure out how to develop this model. Yeah, let me check if there are questions. Yeah, sorry. So I missed one question. Is one hot representation a particular type of bag of words? Um, One hot? No, I don't think so. It's not. No. So the one hot representation, yeah, it's something else. It's just to represent numbers in a way that can be useful for machine learning models, but it's not a bag of words representation. So perhaps both are sparse, but in the one hot representation, you have only one component that is one, and all the rest are zero. Where in the words, bag of words, you have different components that are non-zero. And another question, when using the bag of words on regression, difference between consecutive values of max features is so huge. So yeah, I'm not clear what the question is about. Maybe it's not related, perhaps it's related to a specific task and not necessarily related to a bag of words. Um, and maybe because perhaps some of the features or some of the words are very relevant compared to the ones I don't know, having lower weights. um, yeah, so it maybe it's not a generic observation. I don't think this is a generic observation. Perhaps it's just something very specific to some case. um, okay, what is, yeah, it's not clear, but I think I have an intuition of what you're trying to say. So but I think it's more related to the problem. So perhaps there is one very relevant feature and others that are less relevant. I don't know, it could be a bias in the data, I don't know. So perhaps you can also consider regularization. If you add more regularization, perhaps this effect uh, um, will sort itself out. I'm not sure. Okay, so going on with our discussion. So yeah, if I didn't get the desired answer, perhaps you can rephrase your question and I can come back on it later and provide more details. Okay, going on with the bag of visual words. Okay, I'll try to maybe to finish in time. I'm not sure. Think I'm not halfway there, so we'll see. Um, okay, so what we want here to build is a bag of words model that can have equally good results in image classification and image retrieval. The main problem is how we define these words. We can try to think of of how words are used in text and language. So words are the atoms that form coherent text. So we can also try to find these atomic repetitive patterns in images. And for example, yeah, this can be patterns such as text tones or specific patches that can have some level of um, generality. And when I say generality, it means that they can find we can find them in different images in different locations. So I don't know, pieces of windows, window corners, parts of cars, and so on. And of course, we do not find this identical part in all locations. So the main thing is to try to make sure that when we have this word or this visual word, we recognize it in all of the instances in which it appears. So it can have variations of orientation, illumination, scale, rotation, and so on. So the main thing is to how do we obtain these visual words. So we have these atomic repetitive patterns, but they are not identical in all the locations because there are all these various transformations. So a visual word is actually a group of similar local image patterns. So it's not a single pattern, it's a group of patterns that are very similar. And these visual words are usually obtained by vector quantization or clustering. So we're going to discuss more about clustering in the future lectures, but for now we're going to briefly present an approach on how we can obtain these visual words using k-means clustering. So yeah, the main idea how we obtain the visual words. So first we take our collection of images and we just sample out patches. So this is a representation in which cars are depicted in the same position, so seen from the side. And so we eliminate the problem of rotation, scale, and orientation in this case. So then if we just eliminate these problems, we can sample out patches. We can apply this unsupervised clustering algorithm, k-means, which we're going to present in the next few slides. And we obtain these groups of representative of similar objects, and these are the patches that can be used to represent a document. So yeah, then we can look back and see that, for example, in this image we can represent it as we take all the patches that belong to this image and we build this histogram that is represented as a bag of words. So just as the bag of words model, we can represent this image as a histogram of patches that appear in the image, but we cannot recover the whole image from these patches. So because we lose all the ordering of the patches, just as for the bag of words model. Okay, so the first bag of words like models were studied in on texture classification. So it was used as an approach to model texture. So the idea was to extract patches and then cluster them, and each cluster centroid is interpreted as a texton, so the building block of texture, and then the representation is given based on the distributions of textons in the image. So these are prototypical elements in the image. So yeah, we have the texture recognition task is to recognize these patterns that can can appear in different contexts, like in nature and also on man-made objects like bricks, um, textile patterns, and so on. So the main characteristic of texture is that there is these basic elements that are repeated over the texture. So then we can represent the texture through histograms of these repeating elements. So basically we count how many textons of each type appear in each image. So for example, in this image we have these, we can extract these textons. For this image we extract these textons, and from this image we extract these ones. And then these are the visual words or the textons that we can use to represent these textures. So then when we try to measure the um, histograms of frequencies, we expect that this the histogram for this texture to be biased and to have more occurrences for these textons. This one will have more occurrences for these textons, and an image with this texture will have more occurrences for textons representing this texture. So then when we use these histograms in a classifier, it will be very easy to discriminate between these histograms belonging to different types of textures. So the same can be used for recognizing objects. So here we see examples of visual words that represent the front wheel of a plane. So this is similar in all these images. Here we have the steering of a motorbike. So the visual words can be used to describe object appearance. So this can vary a lot, even among the same class. So we see here that at least for these steering bars have a lot of variation. So local appearance of object parts have actually lower variation. So for these wheels, we see that the variation is smaller than the variation for planes. So here we see planes with different colors, the point, the nose pointing downwards or upwards, and so on. And also for motorbikes, we see different colors, different shapes, but the bars have less variation than the motorbikes. So ideally we want to model to have visual words to represent object parts. So ideally what we want to obtain is to take our image set, to extract features from images, to learn a visual vocabulary or codebook of these object parts, and then we assign each feature to the closest visual word from the codebook. Then we can represent images based on a histogram of the visual word frequencies. So yeah, for example, this object will be represented to this histogram. So here we have object parts like part of a motorbike, skin, eye region, and some part of this guitar. So ideally, when we represent objects as these histograms, we can also use these histograms to do image classification or image retrieval. So for the feature extraction, actually, in order to obtain features that are invariant to scale, illumination, rotation, and so on, there are different image descriptors that can be used. So first we apply a grid of key points on the image, and for each key point we consider the corresponding patch that is centered in the key point, and we extract some features. So from this patch we can compute some a vectorial representation that is robust to changes such as rotation, scale, and variation. So in this example, there are two approaches here. We can either use key points on a grid like this, and this is called the dense bag of visual words. And there are also approaches that consider a sparse key points. So these are selected on that approach. We can compute use image gradients and edge detectors and select key points on the edges in order to minimize the number of descriptors that are extracted from each image. So in this example, we're using a dense grid over the image. And for each image patch, we extract a descriptor. So for descriptors, we can use sift, surf, hog, and so on. So from a different image, we extract another set of descriptors and so on. So this is just kind of equivalent to extracting words from documents and building the vocabulary of words. So here we extract all these descriptors from all the training images. So as I said before, you can use sift or hog and so on. So these are commonly implemented in libraries such as OpenCV and others, so are commonly used now in literature. So we're going to discuss a bit about extracting hog. So from these two, we don't have enough time to present both of them, but we're trying to present one of them. So in order to extract a histogram of oriented gradients, we first briefly introduce gradients in images. So the gradients give us actually the changes in intensity of the function. So for example, for this image, if we go along the red line, the intensity function looks something like this. So the gradients help us to find the locations with big changes. So here we have a slight an abrupt drop in the intensity function, and then this recovers and goes back to the flat region. And so the derivative for this function looks something like this. And these extreme points correspond to edges of the original image. So this point corresponds to going from a high intensity to low intensity, and this extreme point from low intensity to high intensity to white. So this derivative can be approximated on digital images using the numerical approximation for partial derivatives. So the derivative of a function, so in our case the function is the image in x and y. with respect to x, so we can compute the gradients along the horizontal axis or the vertical axis. So this is computing along the horizontal axis. So we add this small epsilon. So epsilon is supposed to go very close to 0 in order to obtain a very good approximation. But for digital images, since images are formed of pixels, the smallest epsilon that we can use is equal to 1. So we approximate the derivative by subtracting the value of the pixel at x plus 1. By subtracting the value of the function in the pixel at location x from the location x plus 1, and then we obtain the gradient with respect to the horizontal axis. So this can be implemented through a filter that can be applied through a convolution operation over the image or a correlation operation. So in order to model this equation efficiently and to obtain the gradients for all the pixels in the image, we can apply it as a filter. So the question to the answer to the first question is yes, we can implement this through a filter. But I leave the second question for you to answer. So what would be the filter components that can model this approximation of the derivative? Okay, so in the meantime, yes, I think it's maybe it's related to the values for max features. So this question answers to Mihai Alexandru. Okay, so I have an answer for Armand. Yeah, I'm going to accept that answer. Can you also write your full name? So I think it's Armand Nicolichoyo, I think, but just please confirm that's your name. Okay, so yeah, actually the filter can be modeled through these components. So if you use a 3x3 filter, the components to model these equation is 1 and -1. So from the location x plus 1, we subtract x minus 1. And we also have to remember that, so actually, to give you a hint, that filters are rotated during the convolution operation by 180 degrees. So in the correlation operation, we do not do this rotation. So this is the difference between convolution and correlation. So if we want to apply the convolution operation, we rotate them by 180 degrees. So when we rotate this, we have -1 for x and +1 for x. But yeah, the answer is acceptable. Okay, so yeah, there are two partial derivatives for the variation on x and variation on y. So now the question that I would like you to answer is to try to figure out which of these, so these are the image gradients for this image, for the two axes, x and y, and try to figure out which one corresponds to the horizontal axis and which one corresponds to the vertical axis. So you can perhaps just answer left one corresponds to x and or y, and we assume that the other one will correspond to the other axis. First is x, second is y, so the answer is correct. So when you compute the derivative with respect to the vertical axis, you emphasize the changes along this axis. So this gives you vertical patterns, and when you apply the filter along the vertical axis, you emphasize patterns or changes across this axis. Okay, so the filters here is 1 minus 1. I think, yeah, this is a trivial answer to question to answer. So in this case, we see that the white patterns with higher intensities when we go from black to white, and lower intensities, so black when we go from white to black. And the same applies here. So if we try to figure out, so for example, look here at the cheek. So when we go from black to white, then we have white intensity. So this means that the filter that is applied here is 1 minus 1. So you can easily figure out this visually. So yeah, depending on how you use this filter, you can use white, you can obtain white and black, and then if you use the opposite filter, you obtain white here and black here. And okay, so yeah, these are the basic filters that you can use, and in practice people use more complex filters such as the Sobel filters, to approximate the derivatives. So this is a vertical Sobel filter, and this is a horizontal Sobel filter, and we can also use filters as the one indicated by Armand. So that's why I accepted that as a good answer. So when we compute these derivatives, we obtain, so for this image we obtain these derivatives, these derivate images. So these values for the constant variation, we have values equal to 0. Here we have large positive values, and here we have large negative values or small values. And when we compute the gradient of the image, so here we have the partial derivatives, and now the gradient is given by the square root of these squared components. And when we compute these, we obtain the gradient magnitude. So now we obtain, so from this image we obtain this gradient that gives us the locations with highest changes. And note here that in this image we also eliminate the positive and the negative edges, so everything becomes positive because we raise every component here to the power of 2. So this gives us the magnitude of the gradient. So how big is the gradient in these locations, and we also have gradient orientations. So for each each location in the image, we can compute the gradient orientation. So the angle is given by the arc tangent of the gradient, the partial derivative with respect to y divided by the partial derivative with respect to x. So this is the formula to compute the gradient orientation. And the orientation is between 0 and 90 degrees for this quadrant, between 90, and so it goes clockwise from 0 to 90 to 180 and 360. Okay, so this is how we compute the image gradients. And we have the image gradient, and well, the gradients are for a given pixel are composed of these two components. So here we have the gradient magnitude, right, and the gradient orientation. So if we have, so the gradients are actually vectors, and they can be represented through magnitude and orientation. So how large is the vector and what's the orientation of the vector. So these are the polar coordinates, and we can also represent them using the direct component. So the gradient can be represented by the two partial derivatives. So a gradient that is, so if we have variation on the horizontal axis, the gradient vector will look something like this. For a variation on the vertical axis will look something like this, and for any other orientation it will be a vector with this. So the orientation is given by the direction with the biggest change, and the magnitude is proportional to the change on the respective direction. Okay, so yeah, I was supposed to ask this question, but I pressed next too soon. So yeah, but it was an obvious question. So the direction of the gradient is perpendicular to the direction of the edge. So this was obvious. Okay, and also the strength of the edge is characterized by the gradient magnitude. So it can be estimated using the L2 norm as we presented before, or using the L1 norm, which is based on the absolute values of the partial derivatives. So these are the basics that we need to know in order to compute the histogram of oriented gradients. So these descriptors can be used in the bag of visual words. So this approach was proposed in 2005 by Dalal and Triggs as an approach for person detection. But it was later used for different applications, including object recognition with a bag of visual words. Okay, so we discussed now about human detection. So the task is to detect people in images and to assign bounding boxes. So they use for each person, they use a window size of 128 by 64 pixels. So they use a fixed size to detect people. Then they divide this image into cells of 8 by 8 pixels, and then they compute image gradients for each pixel. They obtain the orientation and the magnitude. And then for each cell, they compute a histogram of the oriented gradient. So the cells are grouped into blocks then. So the blocks are typically contain 2 by 2 cells, and the blocks can also overlap. So a block contains 4 histograms, and the descriptor is given by the 105 blocks. So for each block, they compute a histogram that is an average of the histograms of the neighboring histograms, and this gives us the Hogg representation. So this is the main overview of the Hogg, and now we discuss about the steps. So the first, from the original image, we normalize it. The approach was tested with grayscale images and with color images with RGB, and they observed better performance with RGB. So for RGB, the normalization that they used is called gamma normalization. So they transform the intensity values using squared root on I think this is they tried an approach without normalization, with square root and with logarithmic normalization, and they obtain better performance with the squared root. Okay, then they compute the gradients, and they get an image that looks something like this. Well, this is an average of the gradients over all the input images. And you can use different image gradients here. And actually for Hogg, they applied this approach, which is slightly faster to compute. And the most important part, how did they compute the histogram of oriented gradients? So for each cell, they considered an orientation-based histogram with 9 intervals. So it divides the intervals between 0 and 180 to 9 sub-intervals, and they consider the orientation to be equivalent with each orientation is equivalent with the one that is opposite to 180 degrees. So the orientation space is all projected to this orientation. So yeah, if you consider that here we have nine components in the orientation histogram, and the cells have 64 components. So histogram is represented by these by measuring the orientations in all these cells. So the contribution of each pixels is directly proportional with the gradient magnitude. So they contribute proportionally to their magnitude. So a gradient that has a higher magnitude will contribute more to its cell. So this is kind of a soft assignment, and this is not the only place where they do this. They actually use trilinear interpolation. So an orientation is not only contributing to its cell, but also to its neighboring cells. And it's also bilinear based on the cells. So for example, a pixel that belongs to this cell contributes to this cell with a higher weight, but it can also contribute to the other cells with a smaller weight. So all these histograms are based on soft assignments. So how exactly does this work? So if you have a pixel with a new orientation at 85 degrees, then this goes, so this orientation is divided between these two beans. So most of it goes to this bean, but part of it also goes to the bean close to it. So the distances, so we consider the centers. So the center is 70 degrees and 90 degrees. So 85 is 5 degrees away from this center, and 15 degrees away from this center. So the weights are inversely proportional. So the contribution to the interval 70 is 5 divided by 20, which is the distance between centers, and the contribution to this center is 15 divided by 20, which is 3 by 4. So this is a soft assignment, and the same happens with respect to the location of the cells and the neighboring block. So if we have this pixel here, we take the distances from the centers. So the center here is -2. Yeah, so for this one also -2 to the left and -6 to the right, and -2 to the top and -6 to the bottom. And the contributions are, so here we have to the left 6 divided by 8, so 6 the opposite divided by the distance between centers, 2 divided by 8 for right, for top, and down the same. And then when we combine these, we multiply the weights and we obtain, so the contribution with respect to the top cell is 9 divided by 16, and so on for the rest. Okay, so the blocks can also overlap. As I said, a block is a group of 2 by 2 cells, and the block histogram is a concatenation of the histograms of the 4 cells inside the block. So in total, a block has 36 components, and the histograms are normalized with respect to the entire block. And since the blocks are overlapping, a cell can belong to multiple blocks. Okay, so for the normalization, they tried different approaches, and the one that seemed to work best was the squared root mean squared error, the root of the square components, the L2 norm. Okay, so here I have a small error, so I have to make sure that this arrow appears with the rest. Okay, so the entire size of the hog descriptor for the entire image is given by the number of blocks, which is 15 by 7, and the number of cells inside the block, and the number of components in a histogram. So the total is 3,000 and almost 4,000 components. Okay, so the descriptors are also very visually informative. So now for people, the descriptors are correlated, for example, to the legs. Most of the gradients are vertical, and actually you can obtain better visual representation if you apply an SVM on top of this visual of this representation on top of hog. So because the SVM puts weights on the representative gradient orientations. So for people, you obtain this representation of a person, and the same happens for I don't know, various people and other objects like the Eiffel Tower, bicycles, and so on. Okay, so this representation, the blocks from the hog representation can be used as descriptors for images. So you can take these vectors and cluster them. So the assumption is that the vectors that represent similar object parts should reside in the same location in this embedding space. So if you apply clustering, you'll obtain clusters that contain representative visual words. So yeah, the visual vocabulary in the end is based on the centroids of these clusters. So yeah, I mentioned k-means and clustering several times during the lecture, but I didn't explain what it means. So in k-means, we have an algorithm that is based on expectation maximization. So we start with a random allocation of centroids. So we just start with the assumption that some of the data samples are the cluster centroids, and then we repeat these expectation maximization steps, which is based on first labeling each vector based on the nearest cluster centroid. So we first build the clusters by assigning each data point to the nearest cluster centroid. And then once we made the assignments, we recompute the centroids, which can shift in a different direction. So we repeat this step until the algorithm converges. And the objective that is optimized is defined something like this. So the distance between cluster centroid and the data sample. So in the end, yeah, what we obtain is each data point is closest to its nearest cluster centroid. So the algorithm looks something like this. So let's say we have this set of data points. So here we use this two-dimensional representation of the data points, but in the bag of visual words, we use visual descriptors that have several components. So the first step is to, let's say we want to have 3 visual words. So this is also a parameter of the model. Typically in practice we use k equal to 1000 or 5000 or something like that. Essentially if in text documents we expect to have around 10,000 or 20,000 words, we can expect the same thing from images. So the k is in the range of 1000, but here we illustrate the example with k equal 3. So we do the random assignment, and then we start with the iterative steps of the expectation maximization algorithm. So first we compute the clusters by assigning each data point to its nearest cluster. So all these points go into the this cluster, these points go into this cluster, these points form a different cluster here with this centroid. So now we have the cluster assignments, and we take all these vectors and compute the average, which is the new cluster centroid. So this is the second step of the iterative algorithm. And now we have these new centroids. Then we remake the cluster assignments. So we assign these data points. So now we can see that the clusters are slightly different. And once we build the clusters, we recompute the centroids. We remove the cluster assignments and recompute the assignments. Then we recompute the cluster centroids. So we repeat this algorithm, these alternative steps, until the algorithm converges. So when it converges, so in this case we have these cluster centroids. We compute the centroids once again. We eliminate the clusters, then we recompute the assignments. And when we observe that the assignments do not change from the previous iteration, it means that the algorithm has converged, and these are the final clusters. Okay, so this is the main idea behind the k-means clustering algorithm. So this is an unsupervised approach to cluster data points. We will discuss more on this algorithm in the next lecture. But first, this is just a brief introduction to k-means, and it was necessary to introduce in this context. So k-means clustering can be used as an independent approach to group data samples, but in this case we use it in this framework to obtain a good representation for images. So actually these, as I explained before, I showed you that you can obtain these average of these image patches. So this can be represented as vectors, and when you compute the average of these vectors, you obtain this average, this centroid that represents this cluster of patches. So actually these centroids can be obtained through k-means clustering. And yeah, you can now represent objects in images with these visual words. So the person can be composed by a set of visual words that contains, I don't know, legs, upper body parts, and so on. So the limitations of the bag of visual words, as for visual words, the representation does not take into account the location of words in images. So it can also be an advantage because, for example, if you want to detect faces, the model is invariant to faces that have, I don't know, different shapes and have, I don't know, the mouth can be further from the nose, so the face are longer or more round and so on. But this can also represent a problem because it will recognize also things that are actually not faces. So the bag of word representation for an image that looks like this will also be recognized as a face. So this is not right. So in order to find to model the locations of features in the image, is that one way to do this is to use a spatial pyramid. So this idea was initially proposed for color histograms. So for example, all these three images have the same histogram representation, but they visually are very different. So this is a natural image, and these are an image with noise, and it's really not any object that you can identify here. And a way to recover this spatial information is to use a spatial pyramid. So on the input image you apply this recurrent division of the image. So you divide it first in 4 parts, then each part is divided into 4 other subparts. So in this case, the spatial pyramid has, this is the first level of the pyramid, the second level, third level, and you can go, I don't know, up to maybe 4 levels. And for each subregion, you compute a bin, and the final representation is a concatenation of all these bins. So what happens is that you obtain, so for example, this image contains different features, and if you look at the level 0 histogram, they have about the same distribution, but if you go at different levels in the histogram, you obtain different histogram representations. So all these, so usually, for example, the black circles tend to cluster in this region of the image. I don't know, the pluses are typically in the upper part, and so on. So you get different distributions of these features across the image, and this is how it looks for a natural image. So for this image, you obtain this representation. For second level, you obtain a different histograms, and so on. Okay, so this can also be applied. So in this example, the spatial pyramid is the example goes on top of color histograms, but the same idea can also apply to the can also be applied to the bag of visual words. So when you go from visual words to the histogram, you can divide the image into bins and compute histograms for each region of the image. Okay, so this explains the pipeline for the bag of visual words. So you take the training images, you apply dense key points or sparse key points, you extract some descriptors like hog and sift, then you cluster them, and you obtain this vocabulary of visual words. So these are cluster centroids. Then you have to go back to the image and figure out each descriptor to which cluster it belongs. So this means that this red descriptor here means that this descriptor was assigned to the red cluster, and so on. And then you just have to count the occurrences in order to build a histogram representation. And then you can apply some learning model, so you can use some classifier or a kernel method to discriminate between different object classes. Okay, so this was my last slide. I tried to go faster in order to try to finish in time. So let me try to go back. Yeah, so I have to also remember to give some points for these answered questions from Armand and Smith. Okay, so we also have one last question from Mihai. So if anyone else has questions, please please ask while I try to answer, so we don't waste any more time. So let me read the question. By regularization, yes. Yeah, when you apply regression, if you find that you have different, so if the weights are very different for your features, and yeah, if the weights are very large for some features, perhaps you're not using enough regularization. So you can choose to if alpha, yeah, if alpha is the regularization parameter for your model, yeah, you can change alpha. So it depends on the model. So for SVM, you have the parameter C. For kernel ridge regression, I think you have lambda, or maybe it's called alpha. I don't remember exactly. So usually you have some way to control the regularization of the approach. So you want to perhaps you want to add more regularization in order to make sure that your model doesn't assign very high weights only to some features. Okay, so other questions? Okay, it seems that we don't have any other questions for today. So, okay, this summarizes our introduction to supervised learning. So next time we'll start our introduction to unsupervised learning and discuss some approaches. And yeah, we will continue until the end of the semester to discuss about unsupervised learning approaches. And yeah, don't forget that I think the deadline for choosing your unsupervised learning project is 7th of January, I think. So this is what I said before, right? So yeah, you have to start perhaps choosing your projects for the unsupervised task. Okay, and I think yeah, that's all I wanted to say for today. Thank you for participating, and see you next week.